Dark Matter and the Invisible Universe, The Hidden Structure of Reality Part 1. Before we begin tonight's quiet exploration, if these slow journeys through the universe help you relax, you can gently support the channel by leaving a like or subscribing for more calm documentaries like this one. It truly helps this quiet corner of the cosmos continue to grow. And now, there is nothing else you need to do. Just breathe slowly, allow your thoughts to soften, and let us drift into the invisible universe together. When we look at the night sky, we see stars, glowing softly against darkness. Through telescopes, we see galaxies, vast spirals of light suspended in space. We observe nebulae, clusters, and distant quasars. It feels complete. But it is not. Everything we see, every star, every galaxy, every planet, represents only a small fraction of what exists. According to our best measurements, all visible matter accounts for roughly 5% of the total universe. The rest is invisible. This unseen majority includes something known as dark energy, and something else even more mysterious, dark matter. Tonight, we focus on dark matter, the hidden structure that shapes the universe silently, without emitting light, without glowing, without reflecting anything at all. Dark matter does not interact with light. It does not shine. It does not absorb radiation in a way we can measure directly. It moves quietly through space, detectable only by its gravitational influence. The story of dark matter begins not with direct discovery, but with something that did not behave as expected. In the early 20th century, astronomers began measuring how galaxies rotate. When observing spiral galaxies, they noticed something unusual. The outer edges of galaxies were moving much faster than predicted. Based on visible mass alone, the stars and gas we can see, gravity should weaken with distance from the galactic center. Objects farther out should orbit more slowly. But they did not. Instead, stars at the outer edges of galaxies moved nearly as fast as stars closer to the center. Something unseen was adding extra gravitational pull. This discrepancy was first noticed in the 1930s by Swiss astronomer Fritz Zwicky, who studied galaxy clusters and found that galaxies were moving too quickly to be held together by visible matter alone. He proposed the existence of dark matter. At the time, his idea received little attention. Decades later, in the 1970s, astronomer Vera Rubin provided compelling evidence by carefully mapping galactic rotation curves. Her observations confirmed that visible matter was insufficient to explain galaxy dynamics. Galaxies were embedded in massive halos of unseen mass. This invisible halo extends far beyond the visible spiral arms. Dark matter acts like a gravitational scaffold. Without it, galaxies might not hold together. Without it, many structures in the universe might not have formed at all. We cannot see dark matter directly, but we can observe its effects through gravitational lensing. When light from a distant galaxy passes near a massive object, its path bends due to gravity. This bending can magnify, distort, or multiply the image of the background galaxy. By measuring these distortions, astronomers can map invisible mass. Time and again, these maps reveal far more mass than visible matter accounts for. Dark matter surrounds galaxies in enormous halos. It fills clusters. It stretches along cosmic filaments. If we could see dark matter directly, the universe might look entirely different, less like isolated islands of light, and more like a vast web of unseen structure with luminous galaxies embedded within it. Computer simulations show that dark matter likely formed the first scaffolding of the cosmos. After the Big Bang, tiny density fluctuations existed in the early universe. Dark matter, interacting through gravity but not radiation, began clumping together earlier than ordinary matter. Because it does not interact with light, dark matter did not experience pressure from radiation in the early universe. It could collapse more easily into gravitational wells. Ordinary matter then followed, falling into these dark matter structures. In this way, dark matter may have played a crucial role in forming the first galaxies. It shaped the large-scale structure of the universe. The cosmic web, stretching across billions of light-years, is believed to trace the underlying distribution of dark matter. Yet despite its immense importance, we still do not know exactly what dark matter is. It is not made of atoms. It does not consist of protons, neutrons, and electrons. If it did, we would detect its interaction with light. Many scientists believe dark matter may consist of exotic particles that interact only through gravity and possibly the weak nuclear force. Candidates include WIMPs, weakly interacting massive particles, and axions, hypothetical particles that are extremely light but abundant. Experiments deep underground attempt to detect dark matter particles passing through detectors. These facilities are shielded from cosmic rays and background radiation, placed deep beneath mountains or inside mines. Sensitive instruments wait patiently for rare interactions. So far, results remain inconclusive. Dark matter continues to evade direct detection. Yet its gravitational footprint is undeniable. It shapes galaxies. It binds clusters. It influences cosmic expansion indirectly. Even our own Milky Way is surrounded by a vast dark matter halo extending far beyond visible stars. The Sun, the Earth, and every object in our galaxy orbit within this unseen gravitational field. If dark matter did not exist, the structure of the universe might be dramatically different. Galaxies might spin apart. Clusters might disperse. Large-scale structure might not form. Dark matter is silent. Invisible. Unlit. But essential. Imagine drifting through space far beyond the edge of the Milky Way. The spiral arms fade behind you. The bright band of starlight dissolves into darkness. Yet that darkness is not empty. Around you, extending in every direction, lies an enormous sphere of dark matter. It does not glow. It does not shimmer. It simply curves spacetime gently, holding the galaxy together. If you could see only dark matter, the universe would appear as a vast, intricate network of faint filaments and halos, stretching across unimaginable distances. Galaxies would seem like luminous beads embedded within invisible threads. Without dark matter, the cosmic web would collapse. Its presence is woven into the universe's architecture. And yet, it remains hidden from direct sight. Its particles pass through us constantly, perhaps billions per second, without interaction. They move through Earth, through stars, through planets, undetected. This invisibility gives dark matter a quiet quality. It does not flare like a supernova. It does not roar like a quasar. It exerts influence steadily, persistently, across billions of years. On cosmic scales, it is patient. Slow gravitational accumulation over vast spans of time. As galaxies merge, their dark matter halos merge as well. Simulations reveal that these halos overlap and combine, shaping new galactic forms. When two galaxies collide, dark matter passes through largely unaffected, while visible gas may collide and heat. This difference provides further evidence that dark matter interacts weakly with normal matter. Some galaxy clusters provide dramatic demonstrations of dark matter's presence. In the Bullet cluster, two galaxy clusters have collided. Observations show that most of the visible mass, in the form of hot gas, slowed down during collision. But gravitational lensing reveals that most of the mass passed through unimpeded. This separation between visible matter and gravitational mass supports the dark matter model. It is one of the clearest pieces of evidence we have. Yet mystery remains. We do not know the particle. We do not know its precise properties. We only know its effect. Gravity does not lie. Motion does not lie. The equations describing galactic rotation require additional mass. Dark matter provides that mass. As you imagine the cosmic web stretching across space, consider how much of reality is hidden beneath perception. Even on Earth, much of nature operates beyond direct human senses. Infrared light, ultraviolet radiation, magnetic fields, all invisible without instruments. Dark matter is another layer. A deeper, gravitational layer. It reminds us that absence of sight does not mean absence of existence. The universe is larger, more intricate, more subtle than visible light suggests. And tonight, as you drift into the unseen architecture of the cosmos, know that most of reality is gentle and quiet. Dark matter does not flash or flicker. It curves spacetime softly. It guides galaxies patiently. It anchors clusters silently. It forms the hidden skeleton of everything we observe. In the darkness between galaxies, in the vast void stretching billions of light years, dark matter threads remain. Even where visible matter is scarce, faint filaments persist. Structure exists even in emptiness. The invisible universe holds everything together. And as we continue this journey in Part 2, we will explore how dark matter shapes cosmic evolution, how it relates to dark energy, and what its existence means for the far future of the universe. For now, allow yourself to rest within this invisible framework. A universe not just of light, but of hidden mass. Not just of stars, but of silent gravity. Most of reality unseen. Yet steady. Consistent. Patient. Drifting quietly through spacetime along with everything else. The visible universe glows softly against darkness. But beneath that glow lies something deeper. Something vast. Something invisible. Dark matter, the unseen architecture of the cosmos. And it continues shaping the universe, calmly and endlessly, as you drift further into rest. If we could somehow remove dark matter from the universe, everything we know would begin to change in subtle but profound ways. Galaxies would spin differently. Some might slowly unravel, their outer stars drifting away into intergalactic space. The cosmic web, which today stretches across billions of light years, would appear far less structured. The large-scale architecture of the universe would be diminished. Dark matter does not simply exist around galaxies. It surrounds galaxy clusters as well, forming enormous halos that extend far beyond visible light. In fact, most of the mass within clusters is dark matter. The luminous galaxies we observe are only small components embedded within much larger gravitational wells. These wells bend spacetime continuously. They hold galaxies together through slow and steady attraction. Without them, clusters might disperse over cosmic time. The influence of dark matter becomes even more important when we look back toward the early universe. Shortly after the Big Bang, the universe was filled with radiation and elementary particles. Ordinary matter was tightly coupled to light. Radiation pressure resisted gravitational collapse. Dark matter, however, did not interact with radiation. It was unaffected by that pressure. As the universe expanded and cooled, dark matter began forming gravitational clumps earlier than visible matter could. These invisible clumps became the seeds of future galaxies. Ordinary matter eventually fell into these dark matter wells, cooling and condensing into stars. In this way, dark matter may have made galaxies possible. It created the first quiet scaffolding. Simulations of cosmic evolution show this clearly. When dark matter is included in models, galaxies form in patterns consistent with observation. When it is excluded, structure fails to emerge in the same way. Dark matter shaped the rhythm of cosmic growth. It determined where galaxies would cluster. It guided the formation of filaments stretching across unimaginable distance. And yet, it remains invisible. Because it does not emit or absorb electromagnetic radiation, dark matter passes through the universe like a silent current. Even two dark matter particles may pass through one another without interaction beyond gravity. In this way, dark matter is different from ordinary gas. When two clouds of hydrogen collide, friction heats them, compresses them, and produces radiation. When two halos of dark matter overlap, they move through each other almost unaffected. This behavior helps explain observations like those seen in colliding galaxy clusters. The separation between luminous gas and gravitational mass reveals a distinction between visible and invisible components. Another line of evidence for dark matter comes from measurements of the cosmic microwave background. This faint afterglow of the early universe contains subtle temperature variations. These fluctuations provide a snapshot of conditions approximately 380,000 years after the Big Bang. The pattern of these fluctuations depends on how much matter exists, how it behaves, and how gravity influences early structure. Careful measurements from satellites such as Planck show that dark matter must exist in significant amounts to produce the observed patterns. In other words, the invisible universe is encoded into the oldest light we can see. Dark matter influences both the early and modern cosmos. It shapes galaxies. It shapes clusters. It shapes the web connecting them. Even within our own Milky Way, dark matter surrounds us. The Sun orbits within a vast halo that extends far beyond visible stars. The gravitational pull from this unseen mass affects orbital motions subtly but persistently. If you imagine floating above the plane of the Milky Way and looking downward, you would see spiral arms of light. But surrounding them would be a much larger, spherical halo of invisible matter. This halo contains far more mass than the stars themselves. Dark matter is not a minor correction. It is dominant. Despite decades of research, its true nature remains unknown. Physicists continue designing experiments to detect possible dark matter particles. Some detectors are cooled to extremely low temperatures, waiting for minute energy deposits. Others attempt to detect tiny flashes of light caused by rare interactions. Large particle accelerators search for new particles that could correspond to dark matter candidates. So far, none have been confirmed conclusively. This uncertainty has led some researchers to explore alternative theories of gravity. Perhaps, they suggest, gravity behaves differently at large scales than predicted by Einstein's equations. However, most evidence currently favors the existence of dark matter rather than modification of gravity. The gravitational lensing, galaxy rotation curves, cluster collisions, and cosmic microwave background all point toward additional unseen mass. Dark matter is woven into nearly every cosmological observation. But what does this mean for the future of the universe? Dark matter interacts through gravity, so as galaxies merge and clusters combine, their dark matter halos merge as well. Over billions of years, these halos become larger and more complex. Eventually, as dark energy drives accelerated expansion, only gravitationally bound systems remain connected. Within those systems, dark matter continues to shape structure. In the far future, when star formation slows and luminous matter fades, dark matter halos will still exist. They will continue curving spacetime quietly. Long after the last stars burn out, dark matter will remain, drifting invisibly. It does not evaporate like black holes. It does not radiate like stars. It simply persists, unless it slowly decays over immense spans of time, something not yet observed. As the universe approaches a state of greater entropy, ordinary matter disperses. Radiation stretches with expansion. But dark matter, unaffected by light, remains gravitationally relevant. Even in a dimmed cosmos, invisible mass shapes motion. There is something profoundly calming about that steadiness. While luminous structures flicker, flare, and fade, dark matter maintains quiet influence. It does not explode. It does not collapse dramatically. It accumulates gradually. If you could stand within a cosmic void, one of the emptiest regions between filaments, you would still not escape dark matter entirely. Even voids contain faint traces, though far less concentrated than in clusters. The invisible web stretches everywhere. Light outlines it, but gravity reveals it. The universe we perceive is only the illuminated surface. Beneath it lies structure we cannot see. Perhaps the most humbling realization is that most of reality is hidden from direct experience. Human eyes evolved to detect a narrow band of electromagnetic radiation. Even our most powerful telescopes capture only specific wavelengths. Yet gravity informs us of what lies beyond perception. Dark matter teaches us that understanding does not require visibility. Equations describe its presence. Observations confirm its effects. Its silence does not diminish its importance. And as the cosmos expands, dark matter continues its role. Galaxies will drift farther apart. Clusters will remain bound internally. The cosmic web may stretch thinner but will not disappear entirely within bound regions. Expansion influences distance, but gravity continues shaping local structure. In Part 2, we will explore how dark matter connects with dark energy, how it influences the fate of galaxies in an accelerating universe, and how the invisible majority may define the ultimate destiny of cosmic structure. For now, rest within the thought that beneath every star, beneath every glowing galaxy, lies a foundation you cannot see. An invisible scaffold holding everything together. A quiet architecture beneath light. Dark matter does not demand attention. It does not shimmer against the night. But it sustains the universe's form. Steady. Persistent. Unseen. And as you drift towards sleep, imagine the vast cosmic web stretching across billions of light years. Threads of invisible mass connecting luminous islands. Clusters hanging like dewdrops on dark strands. All moving slowly within expanding space. Silent gravity guiding motion. Hidden mass shaping destiny. The universe is not empty darkness. It is structured invisibility. And that invisible structure continues unfolding calmly, beyond sight, beyond sound, and beyond urgency. The visible stars are only the surface. The deeper universe is quiet, stable. And, beyond the large-scale expansion of space and the quiet persistence of dark matter halos, there remains another layer of subtlety in the invisible universe. The interplay between dark matter and visible matter does not end with galaxy formation. It continues influencing motion at every level of cosmic organization. Within galaxies, dark matter determines how spiral arms remain stable. Without sufficient gravitational support from invisible mass, rotational motion could distort or scatter stellar orbits. Instead, galaxies maintain coherent shapes for billions of years. Their rotation curves remain relatively flat, balanced between centrifugal motion and gravitational pull. This balance is delicate. Gravity works constantly, but gently. Dark matter does not act suddenly. It accumulates influence through mass distribution. As galaxies evolve, small satellite galaxies often orbit larger ones. These satellites move within the dark matter halo of their host. Over time, gravitational interactions may tear them apart, their stars becoming faint streams wrapping around the larger galaxy. Astronomers have observed such stellar streams around the Milky Way. These streams reveal the shape and extent of our galaxy's dark matter halo. The invisible structure leaves traces through motion. Even though dark matter cannot be seen directly, its presence is mapped through careful measurement of trajectories. In galaxy clusters, dark matter's influence is even more pronounced. Clusters contain thousands of galaxies bound within enormous halos that may span millions of light years. The gravitational binding of such clusters requires far more mass than visible galaxies provide. Hot gas within clusters emits X-rays, yet even this luminous gas accounts for only a portion of total mass. Gravitational lensing measurements consistently show that dark matter dominates. As the universe expands, clusters remain internally bound while drifting apart from other clusters. The large-scale cosmic web slowly stretches. Imagine observing the universe from outside its timeline, watching billions of years unfold like a slow tide. Dark matter filaments emerge first. Baryonic matter falls inward. Galaxies ignite. Clusters gather. Then, as dark energy becomes dominant, expansion accelerates. Filaments stretch. Voids widen. Clusters isolate. All the while, dark matter remains quiet, simply following gravitational law. There is no resistance. No dramatic transformation. Only gradual change across enormous spans of time. Eventually, as cosmic isolation deepens, observers within a galaxy cluster may look into the sky and see only darkness beyond their local stars. Evidence of distant clusters will have slipped beyond the observable horizon. Yet dark matter halos will still hold their galaxies together, even when light from beyond no longer reaches them. This future isolation does not alter the internal structure of galaxies immediately. Dark matter halos do not dissolve simply because expansion accelerates. Gravity continues binding what is locally bound. This means that complexity persists within islands of structure long after the broader web thins. Even when the universe appears mostly empty, gravitational order remains within bound systems. Dark matter provides continuity across these transitions. In some theoretical models, the far future may see the slow evaporation of even the smallest gravitationally bound systems. Interactions over immense time could eject stars and remnants from galaxies, leaving behind primarily dark matter and black holes. Expansion would continue outward relentlessly. If dark matter particles are stable, they would continue curving spacetime quietly within these sparse halos. If they decay slowly, halos might diminish across unimaginable time. But neither scenario implies sudden change. Entropy increases gradually. Structure fades gently. The invisible universe evolves without spectacle. Perhaps the most extraordinary realization is that dark matter has shaped nearly every visible phenomenon we associate with cosmic beauty. Spiral galaxies depend on it. Galaxy clusters depend on it. The very distribution of galaxies across the sky reflects its pattern. When we gaze at deep-field telescope images filled with thousands of distant galaxies, we are seeing light arranged according to invisible gravitational scaffolding. The luminous universe traces hidden mass. Without dark matter, that tapestry would look profoundly different. The quiet majority shape the visible minority. Dark matter does not participate in electromagnetic interaction, but gravity ensures it is never irrelevant. In fact, gravity may be the most democratic force in the universe. Every form of mass and energy contributes. Dark matter contributes enormously. It is patient mass. Mass that does not shine. Mass that does not cool through radiation. Mass that does not fragment in the same way as normal gas. This difference explains why dark matter formed large, diffuse halos rather than stars. It does not clump on small scales because it lacks dissipative mechanisms. It remains spread in broader structures. Ordinary matter, by contrast, can radiate energy and collapse more tightly, forming stars and planets. Thus, luminous structure emerges inside invisible envelopes. The relationship is layered. Halo first. Star later. Galaxy afterward. All unfolding within a gravitational framework set by dark matter. Even now, billions of dark matter particles may be passing through Earth each second. They interact so weakly that they do not disturb atoms or molecules in any measurable way. They pass through your body, through the planet, through stars, without friction, without collision. Silent participants in existence. It is remarkable to consider that we live inside a river of unseen particles, streaming through the galaxy. We do not notice. Gravity works subtly. It requires scale to reveal itself. At planetary scale, dark matter's local effect is negligible compared to the Sun's gravity. At galactic scale, its influence is decisive. Scale defines significance. The invisible universe operates gently in local settings and profoundly at cosmic ones. Looking forward trillions of years, as luminous activity fades, dark matter may represent one of the last structured elements in the universe before entropy smooths everything further. Even then, structure fades not in chaos but in continuity. The universe does not fall apart suddenly. It relaxes. The phrase heat death may sound dramatic, but it refers to equilibrium, not destruction. Dark matter participates in that long relaxation. It helps structure persist long enough for complexity to arise. Then it accompanies structure through isolation and gradual fading. Even in a universe mostly composed of radiation stretched thin across space, dark matter halos, if stable, could remain pockets of curved spacetime drifting alone in endless expansion. Eventually, if dark energy remains constant, distances between such pockets grow immeasurable. Communication becomes impossible. Isolation becomes permanent. Yet each island still obeys gravitational law internally. Even in isolation, structure remains calm. Dark matter does not destabilize structure, it stabilizes it. As we conclude this extended journey, imagine once more the cosmic web from afar. Filaments glowing faintly with galaxy clusters. Dark threads weaving through blackness. Expansion slowly widening the spaces between them. Inside each node, galaxies orbit quietly within halos of invisible mass. No rushing. No collapse. Just slow gravitational choreography. The universe, though vast and mostly unseen, is remarkably orderly. Dark matter exemplifies this order. It does not require brilliance to be essential. It does not require visibility to define reality. It holds galaxies together without announcement. It shaped the early universe without spectacle. It sustains structure without noise. Perhaps the most peaceful lesson from the invisible universe is that stability often lies beneath what is immediately visible. The most powerful influences may be the quietest ones. Gravity, unseen yet universal. Dark matter, invisible yet dominant. Dark energy, subtle yet expansive. All guiding the cosmos gently forward. Tonight, you rest within a galaxy held together by unseen mass. You are carried through space by gravitational curvature you cannot feel directly. The stars above are arranged by structures hidden from sight. And everything continues moving slowly across billions of years. The universe does not strain toward its destiny. It unfolds with patience. Even when most of it is unseen. Even when most of it is silent. The invisible universe stretches far beyond what light reveals. Yet it remains structured, calm, enduring, and steady beyond perception. As expansion carries galaxies apart and time moves steadily forward, dark matter continues its quiet work. Curving space-time, binding motion, shaping structure, all without drawing attention. The luminous universe may fade one day, but the deeper gravitational framework will have defined every chapter. From the first clumps after the Big Bang to the isolated islands of a far future. Invisible, yet fundamental. And beneath that unseen architecture, you can drift peacefully, knowing that even the vastest structures in existence operate slowly, gently, and without urgency. The invisible universe remains silent, stable, patient, and entirely at rest within its own expanding darkness. There is another dimension to the mystery of dark matter that extends beyond astronomy and into particle physics. While its gravitational effects are clear, its microscopic identity remains unknown. For decades, physicists have searched for the fundamental particle that could explain this invisible mass. One major candidate has been the WIMP, or weakly interacting massive particle. These hypothetical particles would have mass and interact only through gravity and the weak nuclear force. If they exist, they would be present throughout the universe in enormous numbers, yet pass through ordinary matter almost entirely unnoticed. Deep underground laboratories attempt to detect rare interactions between dark matter particles and atomic nuclei. These detectors are shielded beneath layers of rock to minimize interference from cosmic radiation. Sensitive instruments measure tiny flashes of light or minute vibrations that could indicate a collision. So far, the results have remained uncertain. Another candidate is the axion, a particle much lighter than WIMPs but potentially far more abundant. Axions would interact even more weakly with normal matter, making them extremely difficult to detect. Specialized experiments attempt to convert axions into measurable photons inside strong magnetic fields. There are also more exotic proposals, including sterile neutrinos or entirely new classes of particles predicted by extensions of the standard model of physics. Yet none have been confirmed. Dark matter continues to exist as a gravitational certainty but a particle mystery. Despite this uncertainty, cosmology proceeds confidently in describing its large-scale behavior. Simulations that include dark matter consistently reproduce the web-like structure of the universe we observe. Remove it, and the simulations fail to match reality. Dark matter is not a minor correction to physics. It is a foundational component. And yet, it remains silent. There is something humbling about that silence. The majority of matter in the cosmos neither glows nor absorbs light. It simply curves spacetime and drifts through existence without spectacle. If we imagine the far future again, as dark energy isolates gravitational systems from one another, dark matter halos may become the final remaining structured regions in a vast cosmic emptiness. Within each halo, remnants of stars may orbit for unimaginable spans of time. Even as black holes slowly evaporate through Hawking radiation, dark matter particles, if stable, could remain drifting within curved spacetime wells. Eventually, as matter interactions become increasingly rare, the universe approaches thermodynamic equilibrium. Distances grow. Particles disperse. Temperatures fall. Yet even at equilibrium, spacetime continues expanding. Dark matter does not resist expansion at the largest scales. It only binds what is close enough. As galaxies drift beyond the cosmic horizon, their dark matter halos drift with them, still holding internal structure steady. Observers, if they existed far in the future, would see only their local halo and little else. No external galaxies. No large-scale filaments. Just darkness beyond. That darkness would not be empty in a perfect sense. It would contain diluted radiation and perhaps scattered particles, but no significant structure. Dark matter reveals something profound about existence. Structure depends on gravity, and gravity depends on mass. Most mass is invisible. Therefore, most structure depends on what cannot be seen. Without dark matter, the luminous cosmos we know might not have assembled in the same way. It is possible that life itself is indirectly a consequence of this invisible mass distribution. Galaxies formed because of dark matter wells. Stars formed because gas collapsed into those wells. Planets formed because stars existed. And consciousness formed because planets did. Invisible mass shaped visible experience. This realization adds quiet depth to the night sky. When you look at distant galaxies, you are seeing only the luminous expression of deeper gravitational architecture. The visible universe is a thin, glowing layer on top of invisible structure. Over the span of cosmic history, dark matter has participated in every major transition. From the early density fluctuations of the primordial plasma, to the collapse of the first halos, to the clustering of galaxies, to the merging of clusters, and now to the slow isolation of cosmic structures under accelerated expansion. It does not initiate dramatic explosions. It does not produce radiation. But it shapes the stage upon which everything else unfolds. Imagine a vast cosmic ocean without waves, only gentle currents beneath the surface. Dark matter is like those currents, guiding motion invisibly. Even now, Our galaxy moves through space within a local gravitational field shaped largely by dark matter. The rotation of the Milky Way, the motion of satellite galaxies, and the subtle bending of light from background sources all testify to unseen mass. Dark matter may never be directly photographed in the traditional sense, but its gravitational imprint is everywhere. Even if particle experiments fail for decades more, cosmology continues mapping its distribution indirectly through lensing surveys and galaxy clustering measurements. The universe has revealed the presence of invisible mass through consistency of motion. And motion does not lie. Looking further into the distant future, if dark energy remains constant, the expansion of space becomes the defining feature of cosmic evolution. Galaxies not gravitationally bound to ours disappear beyond the observable horizon. Local clusters remain intact but isolated. Inside those clusters, dark matter halos remain gravitational anchors. Eventually, interactions between stars become rare as stellar remnants drift through increasingly vast space. Even collisions become improbable. Time stretches across unimaginable spans. And through all of it, dark matter persists quietly. Perhaps, in the most distant epochs, the final observable structures will be faint, cold remnants embedded within extended halos of unseen mass. No starlight. No glowing nebulae. Only slow curvature in spacetime. It is a picture not of destruction, but of calm dispersal. The universe does not end in fire. It does not collapse violently under current evidence. It relaxes. Dark matter participates in that relaxation by maintaining structure locally as the broader cosmos expands. In the ultimate quiet of deep time, even the distinction between visible and invisible may fade in significance. Particles drift at vast separations. Energy differences diminish. Expansion dominates. And gravity, once sculptor of galaxies, becomes subtle against expanding space. But for billions upon billions of years yet to come, structure persists. Galaxies continue rotating. Clusters remain bound. Dark matter halos continue curving spacetime. The invisible universe is steady. It does not rush toward transformation. It allows time to stretch. Even now, as you sit on a planet orbiting a star within a spiral arm of the Milky Way, you exist inside a halo of unseen matter extending far beyond the farthest visible star. That halo has shaped the orbit of your sun for billions of years. It will continue shaping it for billions more. Invisible support. Silent stability. The idea that most of existence lies beyond perception need not be unsettling. It can be grounding. The visible universe dazzles, but the invisible universe stabilizes. It provides gravitational foundation. It gives order to motion. It ensures galaxies do not scatter. It shaped the early cosmos and continues shaping the present. Dark matter is quiet endurance. Dark energy is gentle separation. Together they define the cosmic arc. As expansion continues, the cosmic web stretches thinner. Yet within bound halos, gravity persists. Dark matter remains present even when luminous activity fades. Its particles drift slowly within gravitational wells. In a future of extreme isolation, if one were to observe from within a remaining cluster, they would see dark matter's effect in stellar orbits long after distant galaxies disappear. It is silent structure that outlives brilliance. In the vast timeline of the universe, brilliance is temporary. Structure is patient. And darkness is not emptiness, it is form without light. Perhaps the final lesson of dark matter is this: reality is larger and calmer than what immediate perception suggests. The majority of mass moves quietly. The majority of structure is unseen. And yet everything remains governed by precise laws. No chaos. No unpredictability on large scales. Only gradual evolution across deep time. As you drift towards sleep, imagine the cosmic web once more. Not glowing brightly. but existing as faint gravitational threads stretching across expanding space. Imagine galaxies embedded within halos of invisible matter. Imagine clusters bound gently against cosmic expansion. Imagine dark energy widening distances slowly but steadily. Nothing abrupt. Nothing violent. Only time. Only gravity. Only expansion. The universe is not driven by spectacle alone. It is sustained by quiet forces. Dark matter does not need light to be real. It does not need color to define structure. It curved spacetime patiently, across billions of years. And in doing so, it shaped everything visible. Even now, invisible particles pass through you unnoticed. Even now, your galaxy rotates within a halo you cannot see. Even now, expansion carries distant structures farther away. And through it all, the cosmos remains calm. Stable on large scales. Predictable across time. Dark matter is the quiet architect. Dark energy is the silent expander. Gravity is the consistent sculptor. Time is the patient canvas. And you rest within that vast and invisible framework. Nothing urgent. Nothing rushing. Only gradual cosmic unfolding. The invisible universe remains. Steady. Persistent. Unseen. And entirely at peace within.